Before we begin to start combining resistors, let's go back and remember what our two Kerkoff rules are. So the first was Kerkoff's loop rule, which told us that the sum of the potential changes across all the elements along a closed loop must equal 0. Again, this was a statement of conservation of energy, but it says pick your point, go around any loop you want, all the potential increases that you have plus all the potential decreases that you have, add all those up, you always have to come up with 0 for a closed loop. The second Kerkoff rule was Kerkoff's Junction Rule. And again, so this one says that the current entering a junction must equal the current leaving the junction. This is a statement of conservation of charge. And so current in equals current out. That's our junction rule. So we're going to use these two to initially see what happens when we combine resistors in series. So of course, if we've connected our circuit elements in series, this tells us that the current traveling through each element must be the same. So all the current that travels through element 1 must travel through element 2. And so if I happen to connect my resistors in series, so here I've got a battery. What I notice, of course, is that there isn't a junction, which tells me that the current flowing across resistor 1 has to be the same as the current flowing across resistor 2. So for resistors in series, they must have the same current. All right, let's take advantage of that. So if I know the resistors in series have the same current, I can redraw my circuit. So here, combine them into the equivalent resistor. So again, I'll start in the bottom left-hand corner of this circuit. I'll march across the battery, again going from negative terminal to positive terminal, so that's going to be an increase. And here I only have a single resistor where I have to drop all that potential. So this gives me that the V that I pick up in moving across the battery, all of that has to be dropped across the equivalent resistor. Well, from these two equations, what I can clearly see is that if I combine, I can solve both of them for V. The equation on the left gives me that V equals V1 plus V2. The equation on the right gives me that V equals the equivalent voltage, the voltage across the equivalent resistor. So obviously, if V, the voltage of the battery, is equal to both those two things, they have to equal each other. This tells me that the voltage drop across my equivalent resistor, when I think about R1 and R2 combined in series, that's simply the voltage of R1 plus the voltage of R2. Using Ohm's law, I can now write that V equals IR, and because I know that the current is the same across all these, what that means is the current actually cancels out, and I'm left with my rule for combining to find the equivalent resistance for two resistors in series. The equivalent resistance REQ is simply equal to R1 plus R2. So if I combine resistors in series, the equivalent resistance is simply the sum of all the individual resistances. A couple things to keep in mind. One is that this means that the equivalent resistance is going to be greater than either R1 or R2. So when I combine resistors in series, I'm always increasing what the equivalent resistance of my circuit is. The other thing to remember is that this looks very similar to my rule for combining capacitors, but this was the rule that I had when I was combining capacitors in parallel, and this is now my rule for combining resistors in series. So it's an easy thing to sort of forget and make a mistake with, but make sure that you're using the right equation in terms of combining your resistors in series.